Welcome today in our first video about linear algebra. We will cover several chapters. The first one will be about vector spaces. First, we do the video where we'll cover these four notes, concepts. First thing is set equipped with binary operation, and then we have definition of group, then definition of fields, then some examples of about fields. The second video will be about these three, which will cover vectors, definition of vector space, and also examples of vector subspaces. There are many, endless, and at the end we cover and at the end we conclude some properties of vector spaces. And the third video will be about these three, which will cover vector subspaces, the definition of vector subspaces, and the last video will cover definition of vector subspaces, and also unions and intersections of vector subspaces, and at the end the sum of vector subspaces. First, let's start with definition of set equipped with binary operation. This set we need to define it. So we define a set S, name it S. Then we define a binary operation, which is star, where it takes two inputs and gives you one output. For example, the addition, you have 2 plus 3, it gives you 6. The two inputs are 2 and 3, and the output is 6. So, yeah. So if we have a system where the binary operation is defined for taking two elements from the same set, this means an element from S, X from S, and Y from S, and you apply the relation, the operation, between them, and it gives you an output which is X star Y. This also belongs to S. If we have this system, we can call this set, this is the symbol of a set equipped with binary relation, is S star, like this. We can call this set equipped with binary relation. Operation. By the way, just a note, when we say relation can give you one output, two inputs, two outputs, three outputs, many outputs, zero outputs. For example, this is also a relation, but it's not operation. Operation, it always gives you an output, and this is the difference between relations and operations. All operations are relations, but not all relations are operations. That's it. Alright, let's get started with definition of group. Group is any set that is equipped with binary operation star and has four properties. The first property is closure. Closure is already verified, because if we have a set equipped with binary relation, then you take two inputs from the same set and it gives you a one output from the same set, which is closed. The Sometimes you will see this term in mathematical terminology, which is internal internal relation. So star is an internal relation because you apply it to two sets, two inputs from the same set, and it gives you an output from the same set. And the second property is a identity element. For example, in the real numbers, we have the 1 plus 0 equals 0 plus 1, and it gives you 1. So for R, there is one uniquely E belongs to G, for such that for all X belongs to G, X star A equals A real star X and equals X. The third property is inverse elements. Inverse element is any element that when you do the operation with it between the x and the inverse of x, it gives you back the identity elements. For example, here is it. For all x belongs to G, there is x inverse belongs to G, such this is not we don't mean by to the power of minus 1. This doesn't equal 1 over x. This is wrong in this context. We just mean that x has an inverse, such that x relation inverse of x equals inverse of x star x and equals e. For example, we have the 1, the a plus minus a equals 0. This is in real numbers for the operation, binary operation of addition. All right. Last property is about associativity. I will give you a very intuitive example. For example, 5 plus 1 plus 2. You can begin with these two, and it gives you what? It gives you 6 plus 2. Then you do this, and it gives you 8. Or, in the other hand, you have 5 plus 1 plus 2. If we do this, you get 3. Then 5 plus 3, it gives you 8. So whenever if you begin with this or this, you will get the same result. This is associativity. You begin x star y, then z, it's the same as x then y star z. This is associativity. It's easy, and these properties are intuitive. They don't need a very deep understanding. Just you understand them immediately. Just you have to memorize them to for proving things in the vector space we will talk about. All right. Last thing about groups is commutativity. If we have a set G star is a group, and for all x and y belongs to G, x star y equals y star x. If we have this property of commutativity, we call it commutativity. Utility. If we have this property of commutativity, we call this group as a commutative group. That's it. Alright, let's start with the definition of field. Field is very easy. If we have two groups, f plus f equipped with binary operation of addition and f set equipped with binary operation which is multiplication, if we have these two sets to be in commutative groups, then, and also one condition, for all x and y and z belongs to f, x multiplied by x plus z equals x multiplied by y plus x multiplied by z. This is the distributivity property simply. This is distributivity. Distributivity. If we have these two properties, that these two sets are commutative groups, and for all x and y z with distributivity holds, then f plus dot is a field. Here are the properties of the field of real numbers or any field. So these properties can be used in any field. You can prove them. These are just proofs for these properties. First, that 0 is unique. Also 1 is unique. If a multiplied by b equals a multiplied by c, this implies that b equals c, because we have this, okay? And also if b minus a equals a minus b, then a equals b. Also, if a multiplied by multiplied by any number multiplied by 0 is equal to 0. We proved this by this proof. Also, if a multiplied by b equals 0, that implies that a equals 0 or b equals 0. This is used in a lot in polynomials, solving polynomial that equals 0. So, and also minus a parentheses multiplied by b equals minus a multiplied by b. So positive times negative equals negative. Also here, negative multiplied by times negative equals positive. This is the proof. You don't need these proofs, but I just like to add them for better knowledge. And then you can use these properties for proving any field that is that it's a field, like the one you will see here for the the field of complex numbers, and also you can do that for the field of rational numbers. Goodbye.